Thanks for coming. My name is Prateek. I'll be giving a talk on tape. We'll cover how it works internally. We'll dig into its API and see some real-world examples. So before we get into what a tape is, I just kind of want to explain how we came up about to use it. So I work for a company called Segment. The idea behind Segment is pretty simple. We're a single analytics interface for your app to talk to. You record user interactions with Segment, and we'll send it out to other different tools like whatever Google Analytics, Mixpanel, MailChimp, etc. So it's a little bit like Timber for analytics, except instead of logging trees, you're planting analytics trees, if you want to think about it that way. So because the cool thing about Segment is we actually do a lot of this work on the server, so you don't actually need Google Analytics SDK installed in your app. What this does mean for us is that we take on the burden of uploading analytics data to our servers first. And so we take this responsibility obviously very seriously, because if Segment breaks down, now instead of losing just Google Analytics data, you're losing Mixpanel data, you're losing MailChimp data, everything else you're using through Segment. And so for the purpose of talk, we'll focus on this part. So the API itself is very simple. It's just a HTTP POST request. You send it to a JSON body, which represents a user interaction with your app. And so the traditional way, or rather, Stone Age solution is to just block the app entirely. Maybe this was acceptable in 2010 when Gingerbread was out, but definitely isn't anymore. And it would be kind of absurd if your analytics SDK was doing this to your users. Users don't really care about this. And so offloading these tasks to the background is the right solution to this problem. You can do this either when your app is running on a background thread, or you can just do it in a long-running service. But it's not that easy. Things go wrong all the time. So for example, if this is a HTTP request, networks are flaky. If you've ever driven through a tunnel or walking in an elevator, you'll kind of see your network drop out. The OS might help a little bit, but in most cases, you can't really rely on the network to be up 100% of the time. Just like that, battery life is also a finite resource, so you want to make sure if you're handling cases where the user runs out of battery. And it's also really tricky to actually catch that in QA, or you'll really only run into in production where users run out of battery. And your app might just die because of other reasons, the user might kill it manually. The operating system might kill it, to reclaim memory. So you definitely want to make sure you think about it. You can't just give up. So some apps do give up, and what they do is make the user retry manually. We can do better, and we don't want to do that. The main thing this surfaces is that you can't really rely on your tasks to be left in memory. Just RAM is not durable enough for this. And so the traditional solution to this is put your tasks on disk and you persist them. But before we get into what solutions there are available, let's kind of understand what guarantees we're looking for. So the first one we touched into a little bit already is we want durability. Any element that has been added to the queue will survive. It's in-memory queues are easy to write. You can just use array dequeue or list even. But the problem is those events only stay in memory until the application process is live, and once it dies, your tasks are lost. So you want to make sure that once something's been added to the queue, we can get it later for processing. We also want atomicity. So what this is essentially that either an element is added to the queue or it isn't. There's never a case where the queue is an invalid or partial state, it's not going to have 2.5 elements, for example. And so in the add case, it adds the element or it fails the operation. In the remove case, it either removes the element or it fails the operation. One thing we want to be particularly sure of is if adding a single element fails, the rest of the queue doesn't get dropped because of that. If you're adding a 10th event to our queue, you want to make sure the earlier 9 can still be processed, even if the 10th one fails. And this is not really a guarantee, but this is just nice to have. You want to make sure that our solution is efficient. You don't want your analytics SDK weighing down your app. For our use case, we really just want something that can save to disk, reliably and really quickly. And then we can worry about uploading it later. And we're really looking for a solution that can handle handle these cases and give us these guarantees in the face of things like process dead, system crashes. We want to make sure we have something bulletproof, and obviously like all of these situations are inevitable on mobile. So with these guarantees in mind, let's take a look at what solutions you can get off the shelf, essentially. And not quite off the shelf, like you might have to do a little bit of work to make it work, but we'll see. So the obvious way to persist data to disk is to just use plain Java files. In fact, all the solutions we'll see use some sort of Java file internally. The biggest missing piece of using a Java file directly is that writes are not atomic, so you'll definitely run into a case where your file only contains like partial data, or even worse, like it's in a corrupt state. So the successor to that is atomic file. It's available in the platform since API 17, I think, and it's also available in the support library. And you can just copy it into your source tree if you need to, but yeah, it's in the support library as well. It's just a simple helper that wraps writes to a regular Java file. And essentially it guarantees that writes are atomic by first making a backup of the original file. Then you write to the original file, and once the write is complete, you restore, you delete the backup. So not restore, you delete the backup. So what happens if the write fails? In that case, what you do is you restore the backup. And so its essential premise is that as long as the backup file exists, your main file is corrupt. And if it doesn't exist, your main file is in a valid state. Just as with the regular file, this is probably too low level for most use cases. You'd probably need to write a lot of code to actually make it work like a queue. And a simple implementation would just be to store an array list and serialize it to disk periodically. But the problem with that approach is then you'd end up with keeping all your items in memory, which if your queue was starting to grow large, yeah, you're going to end up using a lot of memory. And we'll see cases where we've actually seen queues grow really large. Beyond atomic file, if you've ever used Android, I've actually seen people use shared preferences as a queue. It's probably the simplest way to persist data to disk. And even though it's really designed just to store key value pairs, you can kind of really use it to store pretty much anything. It's a very high level wrapper around it. Internally, it uses its own implementation of an atomic file, so it does the same process as backing up the file, writing to the original, deleting the backup, and the file write succeeds. Essentially, it writes. One of the problems is, just as with the trivial implementation I suggested earlier, is it keeps this entire map in memory as well. And so if your queue starts to get large, you'll start to see your shared preferences object, you start to use a lot of memory. The other bigger issue is that just shared preference is not actually durable. So when you write to shared preferences, it'll first copy them into an in-memory map, and it'll commit them to disk later. Even if you're using commit or apply, the actual writing part to disk is done in a separate step. And if there is any I/O error during this operation, it actually doesn't tell you. It'll just swallow the error. So you might end up in a case where it's told you, hey, I've added this element to the queue. You're all good, but it turns out it's only in memory and it's not actually durable, it's not on disk, and so you'll lose it when you, if the system crashes or something. And so let's talk about the elephant in the room, the SQLite. So yeah, the traditional way to build queues in Android has been to put it on top of SQL. And this is actually what we did originally in our SDK as well, just because SQLite works great. It's available in the platform. It's atomic, it's durable, and it can store large data sets. But the problem is it really is a database, right? It's not really meant to be used as a simple queue. It's designed for really large data sets that need relational querying, multi-threaded access. And so it's really designed with those optimizations in mind. And what this means is it's really complex. It's got a lot of moving parts, and just we were kind of concerned about using this to break such a critical section for us. If you want to look at an analogy, it's kind of like bringing a bazooka to a knife fight. Yeah, it's just way too big for us. We just needed something simpler, something we had more confidence in and understood way better. And one of the big impetus for us from moving away from SQLite was we were starting to run into a lot of unexplained errors in the wild, and yeah, like because we're an SDK, there's only so much debugging we can do on behalf of customers and devices in particular. So yeah, we wanted just something a lot simpler. And so this is where tape comes in. If you haven't guessed it, it's a library by Square. And for a fun fact, this is actually part of retrofits. If you go into retrofits commit history, you'll see tape before Jake pulled it out. And so tape really checked off all our requirements, really. Essentially what it is, it's a queue-related library, or it's a it's a collection of queue-related classes. And its core component is the class called QueueFile, which is persistent, it's transactional, and it's really fast. And compared to all the other solutions we've seen, it's really meant to be used as a queue, which was which was perfect for us. You don't need to like write your own queue wrappers around it or anything. So before understanding how QueueFile is actually implemented, let's sort of understand what we get from the file system. So first guarantee we get from the file system is that renaming is atomic. What this essentially means is that when you're renaming a file, it either errors and stays as the old file, or it either completes and stays as a new file. You're never in a case where you will have both the files, or even worse, you're never in a case where you have half the data in your old file and half the data in your new file. So this is a pretty important guarantee. We won't get to it in this talk too much, but the way tape uses this is to initialize a brand new queue file. Essentially what it does is it creates a temporary file first, it initializes that file, and once the initialization is complete, it'll rename that file to our real target file. And so if initialization does happen to fail, the temporary file is corrupt for sure, but your real file is never in a corrupt state, and this is a good guarantee. The second guarantee is around durability. So modern file systems are really designed to be fast, like they have a lot of optimizations. What they're gonna do is, when you write to a file, they're not actually gonna write to file directly. They're gonna write it to an in-memory buffer and like store these operations for a while. And like try to batch them on disk, or even if you're doing multiple writes, they might even reorder your operations. So for durability, we really wanted to control, or tape really needs to control the order of operations, and so fsync kind of helps us do that. It's a really low-level I/O operation. It's available on like just the Java file interface. And essentially what the guarantee is that once you call fsync, the operation will only return once all in-memory buffers are flushed onto disk. And there's no really reordering of operations if you're smart. And so those are the two guarantees we saw, and those are pretty standard for most file systems. The one that is very important for tape to work is that segment writes should be atomic. And so this is really the glue that holds like how QueueFile works together, and we'll see how in more detail. But essentially the guarantee ensures that if you're writing data smaller than the size of a file system segment, which is typically in the order of kilobytes, that write can be written atomically to disk. It means either all the data gets written or not. So if the file system segment is 4 kilobytes and you're writing 12 bytes or 32 bytes worth of data, you'll always have those full 32 bytes of data on disk. You wouldn't ever be in a case where only 10 bytes were written, or only like 5 bytes were written. So those are the file system guarantees. On top of that, this is just available in the Java standard library. It's a class called random AccessFile. Essentially what it is a file with a cursor. So you can jump around the file and you can read or write wherever you want. So this is sort of what the API looks like. It's got a seek method, which is where you can control where the cursor is. And it doesn't really have generic methods, but essentially the methods are named readInt, read long, writeInt, write long, etc. And so it just kind of works with like writing primitive Java data to the file. And one of its other tricks is that you can open it in something called RWD mode. And so the Java docs for RWD is pretty simple. Essentially what it does is it opens the file for reading and writing. What it also does is after any write, it'll automatically call fsync, which is what the D is for. I'm assuming it's for durable, but it'll automatically call fsync after every write, so there's no reordering of operations when you're writing. in this mode at least. And so you can really have a full control over how that's handled. And so that's kind of what we have to work with. So let's understand how tape uses all this and how it puts it all together. Tape's internal format, or rather QueueFile's internal format, is very simple. It consists of a fixed size file header, which is the blue portion, and it consists of multiple variable length elements, which are all the green elements, the green items in this. One thing to note is tape or QueueFile is a circular buffer, so anything beyond the blue file header is just a circular buffer. So, for example, your elements could be pretty much anywhere in the file. They're just guaranteed to be sequential. So, element 2 is going to appear after element 1. Element 3 is going to appear after element. Element 3 is going to appear after element 2, and there's going to be no space between elements. But at the end of the file and the beginning of the file might just loop around the circular buffer, like in this case. You might even have element 3 like half at the end of the file, half at the beginning of the file. It doesn't really matter. And so digging into more detail, the file header itself has a very specific format. It's basically 28 bytes worth of data. And just to clarify, this is not actually what is in QueueFile currently. This is Jake's working on it, but this is what's going to happen in V2, and I'll explain what V1 looks like and why V2's version is going to improve some of the stuff. But the file header itself is 28 bytes. It's split into 4 components. The first component is an 8-byte file length. You might wonder why it's stored in the header instead of just reading it from the file metadata. The reason it's stored independently is because once in a while, like tape will need to expand the file because it starts with just a 4 kilobyte file, and so if you need more data, it'll expand that to 8 kilobytes, then to 16, and so on. And to be able to guarantee that that operation itself is atomic, tape needs to store this in the file header just in case it actually did resize the file but didn't have enough time to copy over elements because of something happened in that operation. So storing it in the file header just gives us a guarantee that increasing the file size is atomic. You can read it in the source as well, like it's kind of explained there, but you can ask me if you have more questions. We won't get into that part too much detail. The second component is the count of the number of elements in the file. So this is just the size of the queue. And the third and fourth components are pointers to the first and last element in the file. So in the random access file API, we saw that it had the seek method, and it accepts which position in the file you want to go to. And essentially, these two cursors, or these two positions, give us where in the file the first element is located, where in the file the last element is located. And just to kind of understand how it works, so if, for example, the first element position is 0, what this really means is the count of the file is 0, like there's no elements in the file. And if the first element and the last element positions are the same, like in this case, what it really means is that the count of the file is just 1. It contains 1 element. So you might notice there's this tiny blue bar at the very start. And so this is what's new-ish in V2. Essentially what we call it is the file format version header. It's basically a single bit. It can be 1 or 0. If it's 0, it means it's in the V1 format. If it's 1, it means in the V2 format. V2 format is what we just saw, and this is what V1 format looked like. It's essentially the same. The only difference is the size is the difference. Instead of having an 8-byte file length, or rather 63 bits file length, because the first bit goes to the file version header. And there's 8 bytes for the first element position in V2, and there's 8 bytes for the last element position in V2. So there's nothing wrong with this format, like it works fine. The main issue is that you can only express integers as long as, 4 bytes because of this. So what this meant is your QueueFile could only grow to about like a gigabyte in size. If you've ever run into the dex 64K method issue, this is basically the same thing, except in that case, it's a short instead of an integer. In this case, we were using an int instead of a long. And so yeah, so now we've essentially, by moving it up to 8 bytes, we've increased the size, the theoretical size of QueueFile to, I did the math on this, and it's about 9 million terabytes. So I think in 100 years from now, somebody on Mars is going to be like, what were they thinking? But for now, I think this is okay for us. And in practice, honestly, this change is not a big deal on mobile. I mean, like I said, we've seen people run into cases where files are growing to beyond 2 gigabytes, so they really want QueueFile that can handle beyond 2 gigabytes. But for segments case, like we really just cap our file at 15 megabytes. We don't want your analytics data to like be using too much data on disk, and it rarely even gets to that. Like most of the time, the queue is just empty because we're always processing it and always trying to get all the events onto the server as quickly as possible. It's probably a bigger win on the server. And so remember, tape is a Java library. It's not an Android-specific library. It knows nothing about Android, so you can use it on the server. So maybe that's a place where you might have a better use case for having larger files. So that was the file header format. This is how each of the elements are stored in QueueFile. So essentially, it consists of a 4-byte element header, and then it consists of n bytes of the element itself. And obviously, because the elements can be variable size, because all your data is not necessarily the same size. This is unchanged from V1, like this will stay the same. And essentially, so what we're storing is the length of the element. So in this case, for example, I have some JSON data I'm storing, and it's in 56 bytes, so I store that in my element header. And so that's how tape's format is structured. Let's dig into how it actually uses all this to guarantee atomicity, durability, and even efficiency. So let's take an example of adding an element. Essentially, it begins with a call to QueueFile's add method. It accepts a byte array. And so the first thing we need to do is figure out where is this new element going to go. So remember, tape only keeps pointers to the first and the last element in its header. So in this case, we know that the last element is at position 32. That's what we're stored in the second header. We know the size of the last element, which is 10, and we know the size of the file header, which is 4. So essentially, it becomes, we know that the next element is going to be at 32 plus 4 plus 10, 46, which is roughly, or not roughly, exactly is where element 1 will end. And so we move our cursor to that position, and the first part, we just write the element header. This is just the size of the data itself. And remember, this part actually implicitly calls fsync because of the RWD mode we're opening random access file in. The important thing to note here is if this write fails for any reason, your file is still valid because we're not updating the header, right? So if you open this file again, you'll essentially see that QueueFile still has one element. The first element is still 10 bytes. We're not updating any of the older elements at all. We're just appending to the file. Then once we've written the element header itself, we're going to move by 4 bytes because that's the size of the element, and then we're going to write our actual data. Similarly, similar to the other case, writing this is also, even if this fails, your QueueFile is still going to stay valid. It's not going to get corrupted because the file header stays the same. The rest of the elements are untouched. And this is where the QueueFile magic comes in. So we go once the element is written to disk, we go back to the beginning of the file and we update the header. And remember, the header is 32 bytes in the new version, 16 bytes in the old version. We updated it in one go. We're not writing the file length separately. We're not writing the element count separately, first position, last position. So we just updated all at once. And this is the key to understanding QueueFile. Because segment writes are atomic, and the file header itself is only 32 bytes, which is like way less than most file system segments, which are in kilobytes. We are essentially guaranteed that either this update happens or it doesn't. So if it doesn't happen, you end up with the file you were in the previous state, essentially, where you had one element, and the first position and last position were at 32. If it does succeed, now you have successfully added the second element to QueueFile. And so just to reiterate on that a little bit more, is these are the 3 operations we did before we committed the file header. The way tape works is that the file header is the source of truth. So even if element 2 was added successfully, but not actually updated in the file header, it's not actually going to be visible to you in the queue. Only once the element header is the file header is updated, that's when you can successfully say, hey, I've added this data to disk. And that's really the key to how QueueFile works. So taking the reverse example of removing elements, It's pretty much the same, except the main thing is, so writes happen at the end of the file, and remove happens from the head of the file. So let's just take the file that we had from before. It has 2 elements this time. We call remove. And the first thing, the difference is, because I said completely the reverse, the first thing we're going to do is just update the header right away. So we're going to figure out where the new first position is, which is, in this case, it's going to be where our second element was, which is 46 from our calculations earlier. And of course, we need to handle the case where if there was only one element and the QueueFile is going to be empty after the remove operation, that sort of takes a little bit of its own path. But yeah, once we know where the second element is, and we know that's where the new element is going to be, or the new first position is going to be, we go back to the front of the file and we write the new header, which is essentially decreasing the count of the file by 1, and it's updating the position of the first element. And remember, this again, we're calling fsync right after this. So what this means is either writing the header fails or it succeeds. If it fails, then we're left with the same file as before. But if it succeeds, we're left with this new file, which is essentially a QueueFile with only one element. And again, the important thing to note here is QueueFile is always left in a valid state, even in the case of errors. And so QueueFile goes one step further, and it'll zero out the data that's actually been removed. So it'll go to the old element. It'll write over that with an empty byte array. So essentially, you can think of the first operation almost as a soft delete. And effectively, it is a delete. Like QueueFile is never going to read that element again. But we go one step further and actually zero out the data on disk. And so similar in the add case, the important thing to understand is these 2 files are essentially the same. Even though the element does exist on disk, because it's not referenced in the file header, essentially these 2 files are equivalent, which is they contain only one element, which begins at position 46. It doesn't really matter whether the element 1 exists on disk or not, as if the file header has been updated. And actually in V2, we might add an API where, you can say that, you know what, I don't really care about doing this extra step of removing element 1 from disk. Just leave it in there because this portion's unused anyway. And you don't need to do this extra work to zero it out. And so at a very high level, that's how QueueFile works internally. There's obviously other cases. So for example, you can remove multiple elements from QueueFile. It needs to handle the case of file expansion. Like I said, initialization is handled separately. Removing from a file when it gets empty is also handled slightly differently. But understanding how add and remove works should give you a good understanding of how QueueFile works in those other cases as well, if you read the source. So let's dig into the API a little bit in detail. So this is what I call the core QueueFile API. There's a few more convenience methods we'll see in a bit. And this is actually available in V1 as well. And we're going to keep it for the V2 version as well. But just to walk it through, size simply returns the number of elements in the queue. Add and remove, as we already saw. But just to reiterate, add adds data to the end of the queue, and remove clears data at the front of the queue. And then we have another method called peek. This is also core QueueFile. This is how you actually ask the queue, like, hey, what's the latest element that I should process? One thing to note is that remove does not actually return the element that was removed. You know, like in standard the Java queue interface, it returns the element that was removed when you call remove or pop. And the reason why is we don't want you to follow this pattern where essentially you remove the file first, or you remove the element first, and then you process it. Because what happens in this case if something goes wrong with the processing, right? Well, you can obviously re-queue it, but you might not always get the chance to, and so you would have essentially ended up losing this element. And so don't do this. And I mean, it's not even possible to do this, but don't do this in general. So the correct pattern for using QueueFile is essentially ask it for the element, process the element, and then remove the element. You might ask that, sometimes, so this happens with HTTP or networking related tasks quite a bit, is you might process you might actually successfully make your HTTP post request, but you might not be able to remove the data from the queue just because something happened right after the request completed. And so the way to solve this is with idempotency, and the way we do it is essentially with every task we generate a UUID, and we attach that to that task. And so on a server, if it uses a Redis, or there's two pipelines, so it uses a Redis and DynamoDB cache, and essentially if it sees the same UUID again, it just ignores the second version because it's already processed it, and that's how you guarantee that you're not accidentally posting the same tweet twice, for example. And to take a little bit more real-world example, this is how sort of rough representation of how we use it internally is we ask the QueueFile for a message. We obviously check whether the QueueFile is empty or not. And then we open a connection to our URL. We write the data to the URL, and we close the connection, and we remove the connection. So in general, this is an OK pattern. But because this is HTTP code, we can actually go one step further, and you can actually improve it. The error handling part especially a little bit more. And so with HTTP, typically there's three classes of errors. The first one is what happens if there's a network error? The connection wasn't even able to be made, the user's not connected on Wi-Fi, doesn't have data or whatever. In this case, what you want to do is just retry the error later, or retry the request later. The second kind of error you'll run into is a server error. So what if your server is down? And this is typically represented as a 500 level response code. In this case as well, you want to retry the error later, give the server some time to come back up. And the last case of errors, I remember 200 and 300 are considered good responses, so they're not really errors. But the last case of errors is the 400 level of errors, which is essentially something that's a client-side error. And so in this case, what the best strategy really is to ignore the error. By ignore the error, what I mean is you don't want to retry the same message as is, unless it happens to be 429, which is the rate limiting header. And so in that case, you might be able to retry your request just as is at a later time. But in all the other 400 errors, you really don't want to retry the same request as is, because, for example, an error might be, hey, you're not sending me valid JSON. And if you keep retrying that request, your queue is just going to be stuck because it's stuck on this one element that's really not even valid in the first place. The JSON example is probably not a good example just because it's very unlikely you'll run into that case, but a more realistic example is maybe your auth code expired or something. So you want to make sure you're not retrying with the same authentication token. You're actually updating the token first and then retrying the request. So just make sure you're not retrying the same request when you run into 400 level of errors. And the other important thing, I guess, for us as an SDK is maybe 10 years from now, we'll update our API, we'll break something, and there's still people using Gingerbread and our SDK. So we want to make sure they don't constantly try to hit our servers. So in that case, it's also a good idea to just drop the message in that case. And so this is sort of what it looks like. If there's an IO exception, it's a network error, retry it later. If the response code is greater than 500, it's a server error, retry later. And if it's a client-side error, which is anything greater than 400 and less than 500, don't retry. And it depends on your application logic, but don't retry as is at least. Just give the user the option to amend, for example, or something. And so that was how the core QueueFile API works. This is some of the convenient stuff you have in QueueFile on top of that. Most of this is actually in V1. The only new thing is the iterable interface, and we'll see how that works. So for example, if you're reusing byte buffers, so you don't have to allocate a new byte array for each element, you can use this overloaded method. So you can just tell tape, I have this byte buffer, only read the first 10 bytes in this buffer. IsEmpty is essentially the same as doing size equal to 0. Just do a quick check if the QueueFile is empty. And if you want to remove multiple elements from QueueFile, you have two options. You can either just say, hey, remove 10 elements, or you can say, just clear this file entirely. I don't want anything to do with it. And actually, internally, if you remove equal to the size of the Q file, like it'll actually clear it. The main difference between remove and clear would be whenever Q file detects that the file is empty, it'll actually shrink its size down. And so one of the biggest API changes in QueueFile is that it now implements iterable. It can be used in one of two ways. So you can either do the old way where we were just iterating over the QueueFile. We just keep checking, does it have a next element? If it does, let's get that next element, process it, and remove it. The iterator will actually let you remove elements from the head for this purpose. So this is a pretty good pattern to use if you're running it in like a background service, for example. But the way we use it at Segment is actually we use the batch API where we actually collect multiple elements. Instead of just reading the first element, we read 10 elements from the Q file, we put it into a batch, and we upload it to our server, and then we remove those 10 elements all at the same time. And so for HTTP code, or networking at least, it's good because then you're not waking up the radio for each, you're not doing a network request for each element in your queue. You're actually able to just batch them and upload them at the same time, so it's kind of a good win. So this is what that code will sort of look like. In our very specific case, our server has a limit that it'll only accept 500 kilobytes worth of JSON at a time. So when we're reading the Q file, we just make sure we keep a count of how much data we're reading, and we just stop if we have already read 500 kilobytes worth of data. And so that was the QueueFile API. And so like I said, tape is a collection of queue-related classes. So what in V1 included a bunch of other stuff, but in V2, all this really means is that it has the object queue. And so this is more similar to a traditional Java standard library collection, like a list or a queue. It's a generic class that can hold elements of any type. And so most of the methods on object queue are pretty similar to ones you've already seen in QueueFile. So it's got add, peek, remove multiple, clear, size, etc. The only two real new methods are you can actually say, you know what, just give me the first 10 elements from the queue, and it'll give you that as a list of objects. Or you can just say, you know, just give me a snapshot of this current queue as a list. And you'll probably use both in batch processing. And so QueueFile works with bytes, and object queue deals with plain old Java objects. So the converter is the interface that bridges bytes between objects. If you use retrofit, this is kind of similar to a retrofit converter in that way. And so essentially what the converter does is converts Java objects to bytes before handing them off to QueueFile, and it'll convert bytes to Java objects before returning them to object queue. So object queue itself is an abstract class. Out of the box, you have two implementations. There's an in-memory implementation, which is, I can't remember now, but I think it's backed by a list or an array list or something like that. And so mostly used for testing. Don't really use it in production. And the second is a file-back queue, and so this is what you really want to use in production. In terms of usage, it looks very similar to QueueFile. So you pick data at the head of the queue, do something with it, and remove the data at the end of the queue. Same with the batch processing. You can read data at the head of the queue. You can process it, remove it. You can probably just simplify this example to say queue.addAsList instead of iterating manually. So that's where the convenience API will come in. And so that's tape. QueueFile and tape itself, like they're very low-level APIs. They're really just meant to deal with persistence, and they're very focused. They work on Java. They're nothing specific to Android at all. So one of the issues is you can't really express dependencies really easily. You can't really say, hey, run this task only when the device is plugged in, run this task only when the user is connected to network. You'll need to write a little bit of code yourself to do that. And so if you do need that, these are some of the libraries I suggest you look into. We'll not cover in much detail. Obviously, none of these are solutions for us as an SDK because either we need to add a third-party dependency, and all of these actually are pretty big libraries, or you need to bump up a minimum SDK version. Tape is actually really small. So, and just for comparison's sake, like I said we used SQLite before. A queuing implementation on top of SQLite was actually more heavyweight than copying QueueFile into our library and writing a queue on top of that. So QueueFile is really, really small. So the library options are you can use GCM Network Manager, essentially lets you schedule tasks in the background, and you can define task dependencies, like say only run this task when there's network, or only run it when the user's connected on battery. There's something called the Firebase job dispatcher as well. I don't know what the official Google stance is, but everybody feels like it's been deprecated, so you might want to keep an eye out for that before committing to using this. There's also job schedules, so this is super cool. And there was a great talk by Eric yesterday. The main problem with this, it's only available in Lollipop or above, so you can't really use it if your users are below Lollipop, which I didn't look up the numbers before coming to this talk, but I think for us at least, we're still supporting version 14, I think, and so there's a lot of users still using old versions of Android. But yeah, this is something definitely to look forward to in a couple of years of time, where it's available in the platform, and it really kind of gives you a lot of convenience APIs. There's also this library by Evernote called Android Job. Basically, it's just a wrapper around Job Scheduler, GCM Network Manager, Alarm Manager, and you can conditionally define when to use what. So this is sort of a good library to probably use if you want to switch between all those. And as I said, you probably don't want to use Job Scheduler. You can't really use Job Scheduler in older versions. And so this library sort of handles that by falling back to GCM or Alarm Manager. And the last option is something called Priority Job Queue. So this was developed at Path. It's got lots of features. It's really old library, and it's just been refactored as a V2. And it's still sort of in active development, but it's really pluggable, so that's a really good feature. You can set a customizable queue, you can set custom back off, all that kind of stuff. I forgot to put an ending slide, but that was the end of the talk. Thanks for coming.